So, welcome from my side as well. As I was introduced, my name is Mikael Holmberg. I do come from Extreme Networks, and I'm going to take you guys through Trill and Spb. Let me start with actually asking you, how many of you guys heard about these acronyms? Trill, Spb, PBB. Okay. So I have like 30 minutes, which obviously means it's not going to be a deep dive on technology. My intention is to give you an overview of these two technologies, because at the end I'm going to compare these technologies to obviously, the other technologies you have out there today, like MPLS, VPLS. There's a certain amount of technologies out there. Obviously, as we kind of heard today, these are new technologies. They are not kind of mature technologies in that sense. You can always argue about the fact that, well, a new technology, is it kind of, vendor-specific things you do for certain functions, features, or is it, interoperable with the other ones? But as said, I just want to give you a glimpse of the technologies and then kind of take it from there, comparing these technologies. Obviously, there is a reason for these technologies, right? So I think, this slide kind of gives you an how would you say it, an overview of why. So I guess we all know spanning tree, right? An old technology. There are some flaws with spanning tree. You can read them here, right? You have a blocking port. It's not scalable, so on and so forth. Then you can always argue, well, fine, this is layer 2, right? What if I go IP? Sure, IP probably would solve a lot of problems. Now, here comes the question. There are some limitations with IP, right? Complexity, as well as, from both an operational perspective, as well as from a management perspective, as well as from an implementation perspective. IP adds complexity. Do you guys agree or disagree? Agree? Yeah? Okay. So, having said that, obviously, you're taking a step back, starting to look at what if I'm able to actually, look into those things that IP is so superb in, and then do the same thing with layer 2 technologies, like Spb or Trill. Well, fact being is, it's kind of a layer 2 technology, right? If you look at the OSI layer, it says like 2.5. It's like VPLS, right? Due to the fact that you have a control plane. So, as you guys probably know, both Spb as well as Trill uses ISIs underneath it as the control plane. Which obviously is pretty cool due to the fact that ISIs do not need any IP configuration. It's more or less plug and play. It adds some TRVs, so it adds like functions you need for these specific technologies to, do certain things. So yeah, we all agree on that one. So IP could help, but so let me actually take a step back here and look at this one. So from a layer 2 perspective, you have 6 bridges, you have 8 links, right? The ideal is to use all links, right? All your connections. That's what you eventually want to do. Now, obviously, due to the nature of layer 2, you cannot do that. As we kind of mentioned, like spanning tree, right? You block a certain amount of those. Well, you see some acronyms here. You have ERPS, G8032, a ring technology offer you some kind of traffic engineering. You could always argue, spatial reuse, traffic engineering, all those things. But on a higher level, fine. We all agree that, you lose a lot of connections, you lose a lot of kind of connectivity / bandwidth due to the pure nature of layer 2. Fine. So, looking at this is the ideal scheme, right? This is the ideal world. I have traffic going from E to F. Well, I have 2 paths here, right? I would have traffic going from C to A. I have 2 paths. I would have traffic going from D to B. Once again, 2 paths. Okay, so looking at Spb and Trill, these two kind of layer 2 technologies address this, which is true multipathing. It also addresses things like true shortest path routing. It also addresses things like scalability. What I mean with scalability is, MAC explosion. So you have, a huge forwarding database due to the nature of layer 2 being a flat address space or a flat network. Right? So these three things is something that Spb and Trill address. So true shortest path routing, true multipathing, as well as, handling of your FTPs. Okay. So looking at, from a bridge perspective, if you have full mesh like this one, obviously traffic going from B1 to B3, due to your different protocols, you only have basically a single path here, right? This is not ideal. So what you would like to have eventually is, as you can see, traffic from B1 to B3 would actually have 3 equal cost paths here. See, you go from RB1 to RB5, RB1 to RB6, RB1 to RB7. All have, the same path. You have equal cost paths. So, as said, this is one of the things, addressed in Spb as well as Trill. Now, there are some different flavors in how these are addressed in Trill as well as Spb. I'm going to come to those things later on in the presentation. But this is just on a high level again, kind of put you guys on the map. So, path computation. Obviously, as we see in this picture, what you'll see is unicast path computation. So, what's stated here is, obviously, as I mentioned, Trill as well as Spb is using a Dijkstra algorithm based on IS, right? Which gives you a link level discovery mechanism as well as forwarding mechanism. So what you see is for unicast path here, well, traffic going from F to H always goes FGH, or F to N goes FIK to N. Fine. Now, looking at this on the next level, multipath. Obviously, this would actually allow you to have multipaths. Now, traffic from I to L, you can see that you have 2 equal cost paths. Eventually, you could use both of these paths for your traffic. Same cost. Continue on this one. So here is a small difference now with Spb and Trill. What you see is, as it's done on a hop-by-hop base in Trill, it means that basically I do my decision on a hop-by-hop basis. So looking at traffic from N to C, that's a single hop. Once I hit C, I actually have once again multipath. I have 2 paths with the same cost. So to get from C to B, I could go CAB or CDA. This applies to Trill. This do not apply today to Spb. So the difference being is for Trill, it's done on hop-by-hop basis. For Spb, it's done on an ingress node basis. Once you hit your ingress node, then you are going to actually assign your given multipaths for your traffic. Okay? Now, looking at multi-destination traffic. Obviously, I mentioned 3 key things, for Trill and Spb being the true shortest path routing, being the multipathing, being the FTP explosion, addressing the scalability. Obviously, a 4th thing would be to actually address true multi-destination traffic scalability. So we all know that layer 2 environment as such is not really ideal for how you handle multicast traffic. So in a nutshell, what these technologies address is that you are going to build a complete tree of how you forward multi-destination traffic. So this is just a representation of how you actually would do that. So what you see is that for a given VLAN X in this example, node F becomes your root. So that's the root for your tree. That's how you would then kind of provide connectivity for any multi-destination traffic. So having said that, I think this picture kind of shows it better. So I'm basically building a tree from F becoming my root bridge for that one. Building a tree downwards, what you can see is that you have a couple of nodes here. You have K, G, and L, which have actually members who do not need to receive the multicast. Hence, you are not sending to those ones. So you would pretty effectively prune back on that one. Basically preserve bandwidth and preserve, how you handle these. Okay, so this is like, a really short, high-level overview of some of the key things these two technologies address. You guys follow me on this? Yeah? No? Yeah? Cool? Okay, so that was, as said, just the foundation. Now what I'm doing is just, in a couple of slides, go through Trill. What is Trill? So I guess that this is nothing new for any of you. I mean, Trill is founded by the same, or actually, the one who invented STP is also the inventor for the Trill. You can see what Trill stands for, the acronym. So it stands for Transparently Interconnection of Lots of Links. That's the acronym, right? And it provides you multi-link connectivity from A to B. Now, I kind of already covered this slide shortly, right? So, saying that ISIS was actually decided to be the underlying control protocol, control plane for both Trill as well as SBB. Due to the fact that it's plug and play, you don't need to have an IP address scheme on those. And it also introduced TLB values that can be used for certain attributes within SBB as well as Trill. Okay, so coming basically back to my second slide, where I was saying that, yeah, well, IP would solve, all of these problems we kind of covered here. However, it introduced complexity. Now, the idea of this slide is to kind of give you a view on, if you take the layer 2 switching and the layer 3 routing, you pick and choose the best from both, combine those together, and actually get a technology providing you with, or addressing these limitations or these issues. So what you pick is obviously from your layer 2 switching side, minimal configuration and plug and play. What you pick from your, build came up. Okay, so what you pick from the layer 3 routing is obviously, as we discussed, fast convergence, multipaths, load balance, so really the multipathing, ECMP, hierarchical forwarding, and highly scalable. And I think I kind of, covered all these things already shortly when I described that. The key things that the Spb and Trill address is scalability from a forwarding database perspective. So having said that, obviously we all realize that we talk about the technology or technologies doing some kind of encapsulation. So it's a matter of how you encapsulate stuff when you transport it in both SPB as well as Trill. So obviously you're going to have some kind of a header for transport with both SPB and Trill. So obviously Trill and SPB gives you minimal configuration, plug and play, fast convergence, multiple paths, load balancing, hierarchical forwarding, and highly scalable. Okay? So, digging into Trill a bit more, what you see is basically the Trill header. So what you see is the M bit, which basically stands for unicast or multi-destination frame. So this is where you actually set that bit for providing connectivity, either for unicast or multi-destination. You have a hop count to mitigate loop issues. Then you have something that you see a nickname, right? So basically all your R bridges. So here's an acronym again, an R bridge. An R bridge is actually a Trill enabled device. The R bridge function is to take an Ethernet packet, encapsulate that into a Trill header, transport it, and decapsulate on the other side. This is on a high level what it does. Now, these Trill R bridges work with nicknames. A nickname is a network unique name. So it's network wide. see there's different mechanisms in place how you would then either statically assign these nicknames or they will be automatically configured for you. So on and so forth. So once again, this is on a high level. So on average, that's a Trill-enabled device. Your access VLAN, that's where you're accessing your average. Then you have something called a network VLAN, which is your transport VLAN. Okay, go on to the next picture. So this is basically, your Trill campus network. Always the first thing happening is hellos are established for ISIS connectivity for the averages. So you do ISIS hellos to just do a network topology discovery. You are going to elect a designated average. Now, obviously you're going to exchange your LSPs. So your link level database, are synchronized so you know how your topology looks like, as well as you know all your nicknames, all your VLANs, so on and so forth. And calculate the optimal path for both your unique and multi-destination traffic. And eventually, as you can see in the picture, you are going to have an appointed forwarder, which is the forwarder for a given VLAN. So now, VLAN X and Y, those are the access VLANs, right? You're going to have an appointed forwarder for these given access VLANs to be transported over your network VLAN, which is your Trill encapsulation, to the far end where your decapsulation happens again. Following this, it's high level, but we're all fine with this. So this shows you the encapsulation basically. On the left hand side you have your Ethernet packet coming in. Then you see how your encapsulation takes place. So you see you add in a Trill header and an outer Ethernet header. Obviously you can see for the outer Ethernet header you have a VLAN tag. So this basically tells us that I do forward based on a VLAN. I have my Trill transport VLAN tag. On my left-hand side, the VLAN tag, the .1Q tag, that's something I do not play with within my network side of Trill. Okay, that was Trill. Two slides Trill. We all kind of are on the map what Trill is. Yeah? No? Okay. SPB, same thing, guess what? It's basically doing the same stuff. As said, there are small differences in how you actually do the multi-pathing, so on and so forth. But otherwise, it's a matter of encapsulating things. Now, as you can see, you basically have two flavors of SPB. You have the V and you have the N. Now, I was asking in the beginning, how many of you guys do recall PVB? Provider backbone bridging, AH. Yeah, so SPBN uses MAC-MAC encapsulation, while SPVV uses Q&Q encapsulation. Obviously, having said that, we all realize and understand that SPBN is far more scalable than V, due to the fact that, well, SPVV, I have my limitation of 4,000 VLANs, right, to transport, while SPBN brings me something, an IC, as you had actually in PVB as well, your service identifier, giving you 24 bits, which equals to how many? 16 million service instances, which scales up, right? So I said SPVB and SPBN, and also as said, SPBN is getting much more market traction than SPVB. Now, it's backward compatible with AG being CFN, Y731 being SLA measurements, and so on and so forth. The suite of DCD protocols, ETS, PFC, you name it, all the acronyms there. So it's basically backward compatible with all of these. And as we can see, equal cost. So you have multipath for this one as well, as I kind of started my presentation. Looking at the encapsulation.
Excuse me.
Yeah.
Go back one slide. So it says 16 equal cluster paths. Is this a limitation that comes from the standard, or is this your implementation?
It's a good question. My understanding is this is a standards-based limitation currently. So this is the encapsulation. As you can see, what you'll have is an Spb header, where you basically have a B tag. So now this introduces a couple of new acronyms. On the left-hand side, I basically have my access VLAN, my UniWrite, which is a VLAN with a CBit, the VLAN ID of 20. I map that to an IC, a service identifier of 100. I push that through a bed, a backbone edge bridge, going to a BCB, a core bridge, to another edge bridge. Obviously, I map my CVLAN as a service now with an IC to a BVLAN. And the BVLAN is my backbone VLAN, right? It's my transport VLAN. You're okay with this? Yeah? It's just mapping. Now, obviously, you can have pretty flexible mappings. You could do a range of VLANs, you could do a port-based, you could do a QQ-based, you name it. There's so many different flavors of how you map these to your transport. And what you see is obviously, yes, this is point-to-point connection always. You do not learn MAC addresses on your BVLAN. You only learn MAC addresses for your edge station on the edge bridge. This is something I kind of forgot to mention for Trill. The same applies to Trill, right? You only learn MAC addresses on your access VLAN. Remember the access VLAN and the network VLAN. So any transit Trill or Spb switches do not learn any MAC addresses, host MAC addresses. This is the way to scale up. You only learn on the edge. You do not learn in a transit switch or transit bridge. So that was basically 2 slides on Spb. Kind of got a glimpse, understanding what it is. Now, what I'm going to do is have a couple of slides on comparing these technologies now. So obviously Spb, Trill compared to VPLS, NLAG, a flavor of different technologies. Starting with some kind of a NLAG implementation. Obviously what this gives you is 2 core switches, as you can see the purple boxes. At the edge, you could have a switch, you could have a server, you could have an appliance, anything doing AD, doing link aggregation. You have 2 active paths, right? It could be layer 2, layer 3, northbound. So it gives you basically, full usage of the bandwidth you have. It also gives you redundancy as well as fast failover. Assuming now that my left-hand side link down here goes down, I still have an ISC link, which is the switch-to-switch connection, which obviously is going to pass my traffic once a link goes down. So true active-active, I can only have 2 nodes, right? Now you could argue, how about Trill? Trill would allow you to have multiple core nodes, or if you go in a spine and leaf, multiple spine nodes. I had like 3 in my example, so a way to scale up, right? With more and more spine nodes connecting into leaf nodes, giving you multiple connections after the spine. VPLS, well, I guess we all know what VPLS is. It's an ELAN service, right? So it's a tenant who is seen being on the same LAN across your cloud, providing you a VPLS VSI, a virtual service identifier basically that connects you to the same LAN. You have Spb, as we kind of shortly covered, giving you 60-minute service instances to scale up. Still, it's largely to the domain, as is Trill as well. And this basically shows you, how the layer 2 is really evolving. So starting many years back, you had the 82.1 going to the QTAG VLANs with the limitations of 4K VLANs, right? To address that one, the AD, Q&Q was found where you actually now added a second tag V or SVLAN. So now eventually you have 4,000 CVLANs can be transported with a single SVLAN. Right, so that would scale up for you. You still actually have all your kind of layer 2 issues. How would you deal with loops? How would you deal with, different things? These do not address any of those things. This is purely to scalability in that sense. And then AQ being SPB, right? Where you see that eventually now you have much higher scalability from a service perspective. Okay, so going to this slide. This is basically the last slide comparing these technologies. So looking at the Trill SPB, obviously they are new technologies, right? You can see that one is from ITF, the other one is from IEEE. It's new, right? Even if SPB is a variation of PVB. PVB was around for quite a while, and even before PVB you had PVT, right? With the function of moving the control plane away from the switch, just have the switches down forwarding machine basically. Going back to my slide where I was talking about, why you want to do layer 2 compared to layer 3 routing due to the fact that, it introduced complexity. Now, really going back to the plug and play nature of SPB and Trill, it's pretty much plug and play. As we saw the control plane, it's ISIS, right? So it's plug and play. You don't basically need to configure it. Off you go. And it basically do the network topology discovery for you and all that stuff. So it's really minimal configuration. Always for SPB, you still need to provision your VLANs. So the VLANs. So really your background VLANs. But still, I would heavily argue with you guys that those are simplified compared to if you go VPLS. VPLS, you still have an IGP running your control plane, right? Even if VPLS is a layer 2 forwarding path, you still need to configure all your layer 3 IGP for just the control plane. ECMP, so obviously both Trill and SPB gives you ECMP, multi-path. That's one of the key things. Loop prevention, yeah, with PPL and RPC. And then looking from a scalability perspective from the foundation of layer 2 networks, of bridge networks. Now, obviously, Trill still had a 4K limitation due to the fact that, as you kind of remember, you have your access VLAN and your network VLAN. I'm not addressing by Trill as itself the scalability of the network VLAN. It's still a VLAN. It's still based on the standard of 4K. Now, you could always argue because there are some kind of standards in place or some thoughts about going fine-grained labeling for Trill and all that stuff to actually take the number up from 4K. Looking at SPB, obviously, as I was mentioning, you have 24 bits for ICs, which gives you 60 million service instances. Huge scale. And a key factor is also with both Trill and SPB, any transit nodes do not learn a MAC addresses. This gives you kind of, true scalability from that perspective. So that will basically conclude this kind of short overview of SPB Trill and compared to the other technologies. Are there any questions?